title of the talk is already indicated. My name has been mentioned. And I will deliver this talk, which is part of a cooperation agreement between two companies. The company being my own company, PTIP, which focus on technology development in the CIS field. And the second company, of course, is Singulis Technologies AG. Already a previous talk by Dr. Wolfhard on the commercial development of equipment. This talk is about showing how a technology can be integrated into the equipment in order to produce a viable commercial process. I fully agree with the previous speaker also. I think CIS is the material of the future. Our technology is obviously a little bit different to the Wurth or Mans technology. However, the principles are the same. In the background, we also show the aerial view of our R&D facility in Cape Town, or in Stellenbosch, where we basically focus on the integration of technology and equipment in the same facility in cooperation with Singulis. Just also as a background introduction about our technology, it's been developed over a period of 20 years from a typical academic research facility. In 1993, we already started with the development of CIS, copper indium diselenide. Over a period of 10 years, we changed from CIS to copper indium gallium selenium sulfide, the pentene alloy. We worked on 1 square centimeter, typical R&D scale. In that period of time, over 10 years, I call it this academic phase, we published more than 100 technical papers, filed several patents in the process and product level. Those patents have been granted already in 17 countries, and it basically deals with a novel reaction process to transfer a metal alloy into a homogeneous pentene semiconductor material. Very important, we have always been supported by the South African government, the Science Technology Department, who funded the first 10 years of R&D. And based on the success in the R&D lab, we also received funding in 2003-04 to scale up from 1 square centimeter to 1,500 in our R&D lab at the university. That was very successful. We demonstrated within 1 year that the processes can be scaled to that level. And we actually increased the efficiency from R&D lab to the pilot facility. Very important, the pilot facility obviously scaled the typical technology, materials, but also the equipment. At that point in time, we used batch furnaces for processing, sputtering systems, chemical systems, which we still use today in most cases, but of course at a different level. Very important, in the last few years, we focused a lot of attention on the commercial development of a technology. I was taking it from a semi-commercial or pilot facility into a commercial environment, and for that, of course, one needs a partner. And very important, in 2010, we formed a cooperation agreement or partnership. We actually formed a company in Germany, GmbH company, to focus basically on the marriage of a technology and equipment. That company is Singulis Technologies. We focus mainly on the vacuum technology, the diffusion technology, and the chemical processes, which is the core and the heart of the CIS technology. Also very important, as a result of the cooperation with Singulis, we needed more space, so we relocated our research facilities to a new facility in Stellenbosch. We moved from 100 square meters to 3,000 square meters, and in this facility in Stellenbosch in Techno Park, we have still the R&D labs, the old first generation pilot facility, and a new generation pilot facility, which incorporate the new equipment from Singulis. Also very important in terms of funding and support, the main shareholder of this company today is the Industrial Development Corporation. It's a business unit of the South African government, focused mainly on the commercialization of PV technologies in South Africa. IDC is now a main shareholder of PTIP, and we have received a lot of funding also in the last few months to scale the pilot facility to a semi-commercial facility. Before I discuss the equipment, before you understand the equipment, of course, the equipment has already been described by Dr. Wolfhard. It's important to understand the technology, because the technology needs to be understood in order to develop the equipment. And this is a typical two-step process. We start with a metal alloy. It's sputtered inline, vertically or horizontally. Very important, we control the group 3 elements very tightly in a tight range. And then very importantly, we have a unique Selenization Sulfurization process, always in gas. We use pure gases, hydrogen selenide, hydrogen sulfide. We first start with selenization process, and regardless of the shape or the size of a reactor, you always need to control the temperature and time and concentration of gases in order to form a mixture or an alloy which contain binary and ternary phases. Very important at this stage, commercially, we do it also now on a square meter level. We terminate or stop the selenization process in order to introduce hydrogen sulfide, which then follows this very unique reaction pathway in order to produce a homogeneous single-phase pentane alloy. Very important to understand that we simply control the band gap lattice parameter of this homogeneous alloy by controlling the selenization and sulfurization parameters. It's been demonstrated on a square centimeter level in a batch furnace and has recently transferred to a square meter level in an inline furnace. Why it's important? We control the lattice parameters, therefore we control the optical band gap, and therefore we can improve the device efficiency. That is the process patent. The product patent is very simple. We can produce homogeneous alloys with various levels of sulfur concentration. We simply control the optical band gap by controlling the diffusion process, controlling the degree of sulfur incorporation, and then we produce these homogeneous alloys with different band gaps. This is just an example, and with homogeneous we mean, or we imply, less than 1% variation in the total thickness of alloy. So if you do glancing incidence from top to bottom, you find less than 1% variation in the lattice parameter. This is the more interesting part, just to show our technology development in terms of a diffusion process, which is the core technology, of course. I've shown you the reaction kinetics. And of course, we have developed this process in a batch process from small scale, 1 square centimeter to 6,000 square centimeters. And in the last 2 years, we worked very actively with Singulis to design and to implement a so-called inline process where we transfer the batch concept recipe into an inline concept, maintaining the same material quality and device efficiency. In March this year, or February this year, we commissioned the Singulis prototype furnace in our facility in Stellenbosch. With the assistance of Singulis, we, within 2-3 months, demonstrated that we can transfer the technology to an inline concept. And we have then actually improved the efficiency from a batch to an inline process, not in terms of a device efficiency, but also in terms of a throughput. And on the basis of that sort of result, we have ordered now a semi-commercial line from Singulis, which will be commissioned in our facility within the next few months, early next year. Just comparing quickly batch inline. What is, of course, very important in a batch process, you heat up and you cool down a number of substrates up to 16. The real limitation is the heating and cooling rates. You spend most of the time in heating and cooling. The process dynamics remains the same in selenization and sulfurization, but in total, you can spend up to 7-8 hours in a typical batch process. Divided by the number of substrates, you get to a cycle time of about 45-60 minutes per substrate. Main limitation is this is only the selenization step. You can see we ramp up temperature kelvins per minute. If we go to the inline system from Singulis, the so-called Cesaro system, what is very critical, we can obviously now, using this reaction process we have described and executing it, it's actually very simple. It's more simple than when we developed it in a 1 square centimeter tube. You can ramp up very quickly to a predetermined selenization temperature. And I can just indicate some typical temperatures here, and we just maintain a gas concentration below 1%. So it's a very low gas concentration to control reaction kinetics. And at 450, we have a process time of 12 minutes. At 480, it's 4 minutes. And when we go to sulfurization. This is a typical process we have now developed in the Cesaros. We ramp up at the rate of 1 to 2 Kelvin per second. We go to the selenization process. We do the selenization according to what I've described in the process patent. we interrupt the process. We interrupt it simply by removing the selenium from a tube or from reactor space. We introduce the sulfur at a predetermined temperature. We maintain the pressure at a certain level, and we go to sulfurization. And the total process time is about 10 minutes. And the cool down is, of course, already optimized by Singular's. And within this total time, one can see, for example, heating and cooling is reduced. We still use a typical selenization sulfurization process, but also in that regard, the process time is reduced, and we see a throughput increase or cycle time reduction of at least 50% using the same recipe in an inline process. So innovation, development, R&D goes hand in hand with commercial development. Of course, as already indicated by the speaker, one has to demonstrate to a turnkey customer a process works, the equipment works, and you have a product that works. This was the typical R&D furnace that has been delivered by Singular's to our labs in March this year. We use this furnace, of course, in the inline concept. You have multitudes of these chambers. This chamber was custom built and designed, and the software, of course, recipe structures were designed for the PTIP process. We use a single tube or single reactor on a square meter scale to do a full selenization sulfurization process in gases in order to demonstrate that the reaction kinetics works, that the cycle time can be achieved, and that the efficiency can be achieved. In the inline concept, of course, as already indicated by Dr. Wolfhard, there's two critical factors for the PTIP technology. Is the temperature, homogeneity on the substrate, and its gas distribution. If you control those two parameters, you simply control time, reaction time, in order to control the reaction kinetics. And in the inline concept, between the different chambers, at any position, we can put these thermal scanners, and we can monitor the temperature variances on the substrates, which is typically below 4-5 Kelvin. If you understand the reaction kinetics, you understand how to control temperature on a substrate, you understand how to distribute gas into a reactor, one can get to this very critical result that you can control the selenium incorporation into the alloy in a very tight range. Typically, we aim to get about 40 to 41% selenium in the total module area. The distribution currently is below 1%. We are currently looking at redesigning and improving the reactor, the gas distribution systems, and we think we can still improve on this, but it's still already a very good result. This is the typical morphological features of a pentane alloy after sulfurization. Obviously, we can control the structure of this material by simply controlling the selenization parameters. What's of course key, if you look at the total reactor space of, let's say, 1 square meter, we always look at 9 extreme points in the reactor. We have to control two very important things. We have to control the temperature and the gas distribution. If we do that, we control the reaction kinetics to produce a homogeneous alloy. And this is 9 extreme points where one can see that the selenium distribution is within 1%. But very importantly, the position of the main peak around 27.05, 27.1, we wanted to have optimum band gap. And important, we go at 5 different angles through the materials to evaluate the uniformity in depth. So it's a 3-dimensional view of the homogeneity of your material, and we see less than 1% variation in the lattice parameter over total area. This is, of course, the other important matrix we always look at. So we break the complete reactor into segments, very important segments. We evaluate the absorber quality, optically, electrically, structurally, across the total area. We, of course, control the copper to free ratio. We control, very importantly, the selenium incorporation across the total area. And that always results in a certain alloy, pentane alloy with a certain lattice parameter, which we control. And we obviously try to get the band gap between 1.8 and 1.2 electron volts. And then we, of course, link it to efficiencies. And these are the very first results after commissioning the inline furnace. We produced We took about 3 weeks to optimize the process in order to get the same reaction process in the furnace as we have demonstrated in the batch process. And these were really the first results from that furnace, between 12 and 14%. Okay, this is the system design. And of course, you should speak to Seamless if you're interested in this. This is a furnace we have now designed. And Seamless is busy to manufacture this furnace, which we call the Cesaris, with 100% gas system. So we use the Cesaris concept design. We have modified certain aspects of that furnace in order to demonstrate an inline production process, which will be in our semi-commercial innovation center. We have an entrance section. We just pump, purge, remove the atmospheric residue. We have only one single selenization chamber where we control the temperature and the gas distribution in order to get the mixture of alloys, which we describe in the patent. And then we simply move inline to the next chamber, which is sulfurization. We ramp up the temperature by 100 degrees. We control the gas concentration in that chamber as well. And the total process time here is below 10 minutes to go from a metal into a homogeneous pentary semiconductor material. We have one single cooling chamber, exit chamber, and then we cool down and we move on to the next step. This is the concept for our semi-commercial innovation center in Stellenbosch. Of course, a commercial plant up to 100 megawatts will have 3 of these furnaces. We have typically 4 selenization, 4 sulfurization chambers in this sort of system design, but the physical throughput is simply obviously manipulated by adding more chambers for selenization, sulfurization, but the physical process remains the same, regardless of the number of chambers. Of course, I've already saw this sort of picture. This is the Cesaris, which is currently being built for our technology in Technopark. This is also the type of system we would offer to turnkey customers. And we believe, if you look at this sort of system, what we can demonstrate very, very efficiently is that the PTIP process can be introduced in a commercially established, robust production tool, which is called the Cesaris. We already, of course, will demonstrate improved efficiencies from batch to inline due to superior process control. Very important to understand about material costs and CapEx. We use a low number of furnaces, up to 100 megawatts. The total process time is below 8 minutes, 8 to 9 minutes for the selenization and sulfurization. We use between 0.25 and 0.5 molar% gases in this process, which means a low utilization of selenium and sulfur. And we only use proven engineering principles, which has already been introduced by Seamless into the market. It's a modular design, so we can show you different concepts from 50, 100 to 200, 500 megawatts for this sort of design. And what we obviously demonstrate minimum risk from pilot, semi-commercial to full production scale. This facility is also in close contact with a potential commercial plant in South Africa. And it's the same idea for same concept. This is where we develop improved technology. We transfer from this center to the commercial plants, and we train personnel, and any improvements in our semi-commercial line is transferred to a commercial plant in Cape Town. We are convinced that using this sort of process combined with the Seamless equipment will result in high volume production, secure production, and our turnkey plants are also guaranteed in terms of efficiency and throughputs. And we are determined to go to low capex per watt in terms of this sort of technology. Thank you.